Good afternoon. This is Amy4611, and today I'm your Toastmaster, Lambert. And first, we're starting off with a tabletop question for John Menard. So, John, as awareness of the last male white rhino alive has risen, this brings to question the impact that humans have had on nature. There's various factors for this, like overpoaching or hunting and destruction of habitat. What are some countermeasures that you think we could do? And additionally, do you think that the current damage done to habitats and just species in general could be reversed?
I do believe there are things we could do. Definitely something sort of maybe, opening up our own habitats where, we leave poaching and stuff off limits, maybe putting up some security around there. As in terms of getting it back to the way it was, that's going to be a lot harder. I know they try to do that in the ocean where they put artificial reefs down, and that'll help and then bring back wildlife. There might be something we could do on land for something like that. I don't know about the white rhino, but I think it's kind of going for that. But in terms of lions and things, other species that are endangered, there's definitely ways to make things a little bit more habitable for them as a species and kind of protect them.
And there have been instances already where they've actually set up areas that are no poaching, no hunting for specific species, and it hasn't worked out. Do you feel that there's some way that they can kind of revamp that? And,
I think that would have to really come down to more of a security thing overall. You probably just have to sit out there and really just watch it and make sure poachers don't come in. I mean, people are going to try to sneak in and kill animals no matter how much you really try. It would really take a lot of manpower and money to really form a real security boundary.
All right, thanks, John. And next we have Eric Rohli. It's going to go over the ranking circuit that we have.
Okay, so my name's Eric Rohli. I'm reporting on the ranking cycle. I'm going to move to the other side because the lights in my eyes. And so, ranking cycle, we covered it in thermodynamics a lot. Simple. Water starts here, pumped, goes through a boiler where it's heated, through a turbine where it loses a lot of the pressure, and then in the condenser where it gets back to the normal temperature. One of the most basic cycles in thermodynamics, and really just the advanced cycle. So there's a lot of graphs in this because there's a lot of different places where we can collect data. So I'll start at the boiler. First off, you have to have a fuel for the boiler. In this experiment, we were supposed to use propane. We didn't actually run the experiment because the machine was broken, so I'm trusting the data from another experiment. And as you can see here, fuel flow was fairly normal throughout the experiment. The scale on this y-axis is pretty small, so it looks like it trends upward, but it really more or less constant. As for the temperature of the boiler, there's a constant range here, and then it jumps up dramatically. The reason for that is you're supposed to run it at just the normal state to get it warmed up, and then once it's warmed up, you actually apply the load, and the load causes the temperature to increase. Pressure almost looks like a kindergartner trying to draw a mountain scene, but at various times you had to adjust the pressure with different valves and stuff, and it caused the pressure to go up and down. Again, I wasn't there when they ran the experiment, so I don't know exactly what happened at what times, but as you can see, it just changes throughout the experiment. At the turbine, we had a few interesting things. Temperature at the inlet of the turbine, again, mostly constant at the start as it was warming up. But then after we started applying the load, it was fairly cyclical, going up a bit, down a bit, so forth, until the very end where I guess there must have been a big dramatic pull where it got real hot. And then likewise, pressure, like the pressure in the boiler, varies throughout the experiment. Although in this case, it should be fairly well known that as temperature increases, the pressure drops. So at the outlet, same characteristics as the inlet, except there's only one major jump in the temperature, and the pressure just continues to decrease throughout. As for the generator, current, you're getting a small current throughout. It never jumps up higher than 0.47, 0.48 amps. But I found it interesting that the current was decreasing throughout. just because I figured that as you were getting more temperature and stuff, you might be able to pull some more current. But I mean, that's just the numbers they gave. Voltage, fairly constant. I mean, that's kind of to be expected, especially since the turbine speed was also reasonably constant. So state data, these numbers were just averaged from all of what I had. I had about 15 minutes worth of data. So I just ran an average because it would be nearly impossible to do it for every single second, or every 0.2 seconds, because it was every fifth of a second that it sampled. So temperature, I mean, fairly high in the boiler, what we've come to expect. I found it interesting here that the pressure and the temperature didn't exactly match up on the steam tables. So in most cases it was a little high. There was no data at the outlet of the condenser for some reason or another, so I just kind of assumed that the temperature stayed the same, which probably a bad assumption, but yeah. And calculated values, there were a bunch of values that we had to calculate, of course. Rankine cycle, as y'all might remember from class, we had to do a lot of work to solve it. So heat flow, got about 94 kilojoules, turbine work about 57 watts or so. And efficiency of the generator seemed pretty high, which when I Googled, it agreed that generator efficiency is usually high. Likewise, the thermal efficiency for the whole cycle, 0.377 is the value I calculated. I know Tyler said that for high-end cycles, it runs around 0.4 when he was doing his introduction lead. And he also said that it should be a little bit lower because we're not high-end. It's a nice machine, but we're not making electricity or anything like that. It seems reasonable, and all the numbers on here also seem reasonable. So with that, I'll hand it over to Davis. Introduce.
Thank you, Eric. And next we've got Alec that's going to be going over the IC engine for next week's experiment.
All right, my name is Alec, and I'll be talking about the experiment for next week, the IC engine. So the IC engine is something that most people see in their lawnmowers, their cars. It's a very common engine. It uses fuel. It takes that fuel, ignites the fuel either through spark or by compressing it. With that, the gas expands and creates mechanical work, which then can power your appliance. So one of the most common is a four-stroke engine. So a four-stroke engine works to where it has an intake of fuel and it intakes and then compresses it. With this compression, it actually creates an expansion of the gas, and this is what we use as mechanical work, and then it then releases. And so that is the four-stroke. And I will go ahead and actually show y'all a little example of that. So what you're seeing is it come in, compress, and then expand. The orange is the expansion. And then at the last part, it releases. And so the engine that we'll be using in our experiment is a 13 horsepower OHV single cylinder Predator engine. It is a type of IC engine, and it is four-stroke, which is 2 revolutions per stroke. As you saw before, you have 2 revolutions. So an engine produces power by providing the rotating shaft, which comes from the mechanical work, and the torque then creates the power. So in order to determine the amount of torque that comes from an engine, we use a dynamometer. And the one that will be used in our lab is the Land and Sea dynamite. And so what we will go on over real quick is the auto ideal cycle. So ideally there be no loss of energy to heat, etc. So as you can see for here is the intake is right here, yes. And so then you have not a constant volume, not a constant pressure. Then the combustion process happens at constant volume, constant volume, but not constant pressure. Here we have the power stroke, and then the rejection. Now, the ideal is this here in yellow. And so you can see we have loss and it doesn't come around perfectly as you see in an ideal. So there are many misconceptions between horsepower and torque. So I will tell you first how they're related. So power is the rate of work, but it is dependent on torque, and they are not the same thing. Torque is the measured engine output, or basically how it turns. And so then here's a graph of just ideal torque versus power and RPM. So you have torque on the left, right is power. They both depend on RPMs, but power depends on torque, and torque does not depend on power. So what is horsepower? Horsepower is just a unit of power, a very large unit of power, specifically 33,000 foot-pounds per minute. Now this here is how torque is related to horsepower, which is torque multiplied by the RPMs divided by 5,252. So as the RPMs raises, so does the power. So any questions on that? All right, and I believe that is it. I will hand this over to Davis.
Thank you, Alec. That concludes today's presentations, and next week we'll be having an experiment.